Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. My name is Jay Lorch, and here's Jeff Pang. He's going to be giving a practice talk for our SIGCOMM paper. Jeff Pang will be graduating soon. His thesis is on wireless privacy, but he's also done a lot of work in other networking areas, including games. So I'll let you hear for yourself about the Donnybrook project.
All right, thanks, Jay. So as Jay said, I'm Jeff Pang. And this is joint work with my colleagues here at Microsoft Research and my colleagues at Carnegie Mellon listed on this slide. My advisor, Srini Sessions, is also in the back of the room if you want to ask him more about me later. So multiplayer console games are now often hosted on peers participating in the games themselves rather than on dedicated servers in order to save costs and to reduce administrative overheads, etc. However, this often limits the scale of high-speed games, such as first-person shooters, to 16 or 32 players. For example, games like Halo 3. Large-scale games, such as massively multiplayer role-playing games like World of Warcraft, shown here, are also very popular, and they support thousands or even tens of thousands of players. But currently, they require large numbers of dedicated servers in order to support all these players playing in the same game worlds. So far, no game architecture has been able to support games that are high-speed, large-scale, and peer-hosted. The question we ask in this talk is whether we can achieve all three. To understand why this problem might be hard, let's consider an example. In peer-to-peer games, objects in the game, such as the player avatars, like those shown here by the Xboxes, are hosted on the peers themselves. Sometimes a peer acts as a server, and all the objects in the game are hosted on a single peer, and this replicates a single client-server system. However, we're going to look at the case where each peer hosts its own objects, such as its own player avatars, so that we can leverage the bandwidth resources of all the peers in the system instead of just one of them. So in such a system, each peer sends updates about its objects to all others so that everyone can create a replica and render the current view, as everyone has to see the other objects in order to play the game. In high-speed games, interactions between objects, such as when one player shoots another, have to be reflected very quickly. And this is because it would be jarring if you shoot someone and they sort of explode 2 seconds later. And otherwise, that would make the game sort of no longer fun if interactions were occurred in a delayed fashion. This implies that each peer has to send updates very frequently to every other peer in the system so that when interactions do occur, they appear consistent for the players involved in the interaction. In practice, updates for first-person shooter games and similar genres are sent to every player 20 times per second, and this constitutes approximately 16 kilobits per second per player for every player that joins the game, and this is the amount every player has to send to each other. Moreover, every update has to be delivered within approximately 150 milliseconds, which previous user studies have shown is about the tolerance that is available before it starts impacting or degrading gameplay. Finally, to achieve large scale, a copy of each update has to be delivered to each additional player that enters the game. And thus, the aggregate upload capacity needed in order to support the number of players as it grows scales quadratically with the number of players. Because of this high update rate, the constant factor, which was shown in the last slide, is also very large. So this means that we have to spend a very large amount of bandwidth if we want to send all these updates to all the players. Previous work has tried to address this problem by using a technique called area of interest filtering. Some game worlds can be partitioned into a number of different regions or different areas, and generally players only need to receive updates about those objects or other players in the same regions, for example, in the same rooms here. This is because those are the only players that might be visible, and thus those are the only objects which they might be able to modify or might modify them. However, area of interest filtering can't help when the map can't be partitioned, as some of the maps I'll show later in the talk, or when the game developers want to engineer a large-scale game event, such as a large-scale battle or something like that. Furthermore, it's been shown that in both large-scale and small-scale games, such as World of Warcraft and like Quake 3, which is the map I've shown here, that even in maps that can be partitioned, the population in different regions in a partitioned game world follows a power law. And this is generally because games are social environments, and social networks follow a power law. Thus, if there are thousands or even tens of thousands of players in the same game, then there might still be hundreds or even 1,000 players within a single region of that game. So the goal in this talk is to try to achieve 1,000 players within the same area of interest. This graph here shows the maximum number of players we can support as we increase total upload capacity per peer in the system, the average upload capacity per peer in the system. And this is shown we increase the upload capacity on the x-axis here. The gray line here shows how far we can get using the existing approaches I just described. These blue boxes give you a sense of where we are today. Clearly, if we only rely on home broadband users, which is represented by the blue box on the left, we can't even reach maybe even 100 players. Even if we were able to aggregate the bandwidth of all typical peers in a game, such as if we included peers maybe at universities or corporations that might be able to contribute a large fraction of their bandwidth and make up for the low bandwidth of the broadband peers, we would see here that even aggregating this mean bandwidth of all the peers, which we looked at using a real empirical bandwidth distribution, which we described in the paper, we still don't get anywhere near our goal of 1,000 players. If we try to play this game without enough upload capacity, then the game becomes very choppy and unsatisfying. For example, on the left shows an ideal case where we have enough upload capacity to send the updates for peers, all the peers in the game for a 32-player game in this large map, or this relatively small map. Sorry. On the right shows the same game played on a low-speed cable modem, and you can see that player movement is much more choppy and it's not as smooth as shown on the left-hand side of the screen. For example, if you look at the players jumping through the air, you can see that sometimes they sort of warp between positions rather than flying smoothly between them. And this makes it very unsatisfying. And if you ask a first-person shooter player, they'll say that maybe this is almost even unplayable. This effect, of course, grows worse as we increase the number of players in the game. We only have 32 in this game here. So in the remainder of this talk, I'm going to present our solution, which we call Donnybrook. Donnybrook uses two main novel techniques in order to achieve large-scale, high-speed peer-to-peer games. The first, I'll describe intersets, which is our technique in order to reduce the mean bandwidth demands in the system so that we can hope to scale to 1,000 players. So, because we obviously can't increase the bandwidth capacity of hosts in the system without actually giving away free bandwidth. Second, I'll describe a novel update dissemination strategy which allows us to handle the extreme heterogeneity in both interests and bandwidth capacity of hosts that exist in peer-to-peer environments for games. And finally, present a few evaluation results. So the intuition behind intersets is that even when many players are visible at once, a human can probably only focus or pay attention to a small number of those objects at once. So we should only need to have high accuracy or high fidelity replicas of those objects I'm paying attention to. And other objects can be portrayed much less accurately because I'm not paying attention to them, so I may not notice. In Donnybrook, we define the interset as the 5 players I'm paying the most attention to. And we picked this number based on some playtesting of our own and some cognitive studies like those listed here. I subscribe to the players in my interset, and I receive frequent updates from these players, while I only receive infrequent updates, 1 update per second, from everyone else. So I receive the ideal rate of updates from the people in my interset and about 20 times less updates from everyone else. Players that are not in the interset, of course, receive infrequent updates, and in order to represent them without choppy and jarring movements, we basically use a lower accuracy replica, which we describe in more detail in the paper, but I don't have time to go into detail here. Basically, we use existing AI techniques which exist in the game in order to smooth the transitions between the less frequent position updates. Of course, the main question is how we can get the game in order to estimate player attention, because obviously the player isn't going to tell us what he's paying attention to. In order to do this, in Donnybrook, we leverage the fact that there are several measurable metrics in the game which are often correlated with player attention, especially in first-person shooter and similar genres where the objective of the game is fairly well known. We basically compute the attention as a weighted metric of these three of these metrics, First is proximity, because I'm more likely to focus on players that are closer to me than those that are farther away. Second is aim, because I'm more likely to focus on players that I'm trying to aim at or that I'm trying to shoot at, and thus they'll end up more closely to the center of my screen. And finally, we use interaction recency. That is, we're more likely to focus on players that I've shot recently or that have shot me recently or otherwise interacted with them. And this is depicted with the little animation on the right-hand side here. So we found that these simple metrics are fairly good indicators of player focus in a game like Quake 3, and we did a little bit of playtesting to basically evaluate this. Just to illustrate, let's look at a simple Quake 3 game. So here the players in my interest set are glowing, and they have this little marker over their head. And of course, we wouldn't actually show this in a real game. We're just showing this for illustration here, so we don't actually give away to the player what we think they're focused on. These players are in my interest set because they're closer to the center of my screen, as you can see, and they're also closer to me compared to the other players that are circled in gray here. So we use both the proximity and the aim metric in order to determine these players here. Of course, as I move around and I follow the player I'm trying to shoot, my interest set changes, but generally the player I'm trying to shoot, you can sort of see remains in my interest set. And probably the players I'm paying most attention to in this sort of large melee here are the ones that are closer to me, and thus they're the ones that enter my interest set. Of course, sometimes I'll pick up a sniper weapon, and then instead of proximity, aim will become much more important to those who I'm paying attention to. And you can see in here, even though like one of these players is closer to me than the others, because the others are closer to the center of my screen, the aim metric dominates in this case because I'm using the sniper weapon, and those are the ones that enter my interest set. And this makes it so the game can replay the players I'm paying attention to with higher accuracy, and thus when interactions occur, such as when I shoot this player right there, they will appear much more consistently. Of course, the real question is whether interest sets can improve fun in low bandwidth settings when we otherwise wouldn't have enough bandwidth to send updates to all the peers in the system, and how closely they can approximate a game in a high bandwidth ideal setting. To answer these questions, we conducted a user study with 44 pairs of players. And they played the game I just showed, and each pair compared two of three versions, which are listed on this slide. A low bandwidth scenario using conventional approaches, which I described at the beginning of this talk, a low bandwidth setting using interest sets, which I just showed, and a high bandwidth ideal setting where we have enough bandwidth to send all the updates to everyone in the system using conventional approaches. This graph here shows one of several metrics in our paper that basically all support the same conclusions. The x-axis here shows the version used in each head-to-head, shows the two versions we use in each head-to-head comparison, low bandwidth versus low bandwidth interest sets and low bandwidth interest sets versus high bandwidth. And the y-axis shows the fun score which players gave to each version after they played the two versions. And the error bars here show 95th percentile confidence intervals. We see that players clearly prefer the interest set game in low bandwidth settings to the non-interest set game. And we also see that the difference between the scores in the ideal setting with interest sets or without, even with higher bandwidth, is statistically insignificant. As you can see here, that the error bars basically overlap. So basically, this initial user study, from this initial user study, we conclude that it seems that interest sets effectively preserve the fun gameplay, even when there's not enough bandwidth to send all the updates to everyone in the game. So here we again show the scaling graph, but here the red line shows how far we can get if we add interest sets to the conventional approaches we described earlier. The bandwidth demand is still linear per player as it was before because we still have to send infrequent updates to everyone in the system. However, we only have to send 20 updates, that is the frequent updates, to 5 other players in the system. That's a constant number of players rather than a linear number of players as before. So that the constant factor of the linear scaling is much lower than with the conventional approaches. So we can see that we can probably support several hundred players even if we only had to use ever needed to use broadband capacities for peers in the system, but we still need to leverage the higher bandwidth peers in the system if we wanted to match our goal of 1,000 players in the same region. So some ways we need to be able to aggregate the bandwidth in order to get the expected mean, which is, remember, shown on the x-axis here.
When you're sending an update, what are you sending? Is it actually the bitmap, or is it some coordinates or something?
Right. So it's basically usually coordinates, but it's basically a delta-encoded map of all the fields of the object that which changed during the frame. So every frame, some number of fields in the object changed, like position, and that's what's shipped over. Does that make sense?
Well, I'm just sort of struggling as to, I would have thought most of the rendering is being done local, so the amount of data that's being sent would actually be very small.
Right, it's not so much the amount of data as the frequency of data that's actually very high, because it's 20 updates per second, so even if you're only sending 3 floats across for the position, then that's still fairly high because you have there's packet overhead and other stuff that makes it so you're sending maybe 100 bytes every 20th of a second.
Well, these networks are perfectly capable of keeping up with speech rates, which are faster than that.
Right, and here you're sending it not only to one other person, but you're sending it to all the other players in the game. So if you have 1,000 players in the game, using conventional approaches, you have to send that amount to all those 1,000 players, and that's why the scaling makes it much more expensive. Does that make sense?
I still would have thought I could do a speech bridge with 1,000 people without much trouble.
Okay, maybe we can discuss this afterwards. Okay, so obviously the next step then is to describe Donnybrook's update dissemination scheme in order to handle the heterogeneity I just described. So the first problem, of course, which I just described, is that while the mean bandwidth may be sufficient, some peers have much less bandwidth than others and still don't have individually still don't have sufficient capacity. A second equally important problem is that interest is not uniformly distributed. Suppose I'm the non-eyeball player here, shown on the right. We have one other player paying attention to me now, so I'm maybe in his interest set, and I have to send updates to that one other player. But suppose I pick up an important item, such as a flag in a capture the flag game, or otherwise become more important to the other players in the game, and thus at this point, many more other players will probably start paying attention to me, and I'll enter all of their interest sets. This means I now have to send updates to all of these other players, and thus I may not have enough capacity alone in order to send updates to these players, even if I have high capacity. The conventional approach in order to deal with this problem is to use an overlay multicast scheme. High bandwidth peers basically can help forward updates for lower bandwidth peers, and in order to make up for the lower bandwidth. For game updates, we have 4 main requirements in the overlay multicast scheme. First, we require that there be a strict delay bound because game updates, if they're staler than 150 milliseconds, basically start affecting degrading gameplay. Second, group membership changes very frequently in games because remember that our groups are basically defined by the players are basically defined by the interest sets and who we're paying attention to, and because games are fast-paced, attention changes very quickly. Third, we have bandwidth heterogeneity, as I just described, and finally, we have many overlapping groups because every player in the system acts as a source of a multicast group. The problem with existing approaches, such as those listed on this slide, is that they generally require subscribers themselves to find good places to join in the multicast tree. For example, this eyeball here, if he wants to join my group, then he have to figure out himself where he wants to join as a leaf node or internally in my multicast tree. In unstructured approaches, this generally requires a lot of coordination overhead, which we can't amortize because our groups change too frequently. In video streaming or audio streaming, this is generally okay because we can take the time to optimize the tree, and because players will generally join the group for the length of the video or the length of the audio stream, which is generally much longer than the time we have for games, which a player might only join a single group for a couple seconds. In structured approaches, such as those using DHTs like Splitstream, node placement it takes less coordination, but is generally much less flexible, and thus makes meeting the tight delay bounds we require for games much more difficult. So instead, we take the following approach. We have well-connected peers join a forwarding pool, and nodes detect locally whether they're members of this pool using relative bandwidth and latency thresholds, which are described in more detail in the paper. These nodes advertise their spare capacity to all the others in the game, and we can piggyback these updates on the low-frequency updates, which you'll recall are sent to everyone in the game once per second. And we describe in the paper in more detail how we distribute these updates in a scalable fashion. Finally, when a low bandwidth peer needs more bandwidth to send its updates, it randomly picks enough forwarders in this pool in order to satisfy its needs. And of course, all the peers in the system do this, and they each randomly pick forwarders in an uncoordinated manner. Since a node's subscribers may change very frequently because as I enter someone's interset, such as this red guy here, I'll need to send updates to him as well. This node carries out this process every game frame, so basically 20 times per second. So my multicast tree might actually change during each frame, and I'll pick a different set of forwarders every 20th of a second. This approach basically allows us to more easily meet our delay bounds because we can fix delay tree depth to 2. Basically, we maintain that we only send updates through one forwarder and don't forward it through anyone else. There's no overhead to handle frequent group membership changes because tree construction is basically uncoordinated. Remember, we pick the forwarders randomly without any coordination with our neighbors. And bandwidth heterogeneity is supported because using relative delay thresholds to determine the forwarding pool, relative bandwidth thresholds. And overlapping groups are supported because forwarding resources are shared between all the players in the game. So thus, using this approach, we meet all 4 of the requirements for forwarding game updates. The main trade-off we make using this approach is that many sources may randomly pick the same forwarder during a single frame. And if a forwarder advertises 10 say 1 megabit, and 2 players believe it as 1 megabit and actually send 1 megabit of updates to that forwarder, then it obviously won't have enough capacity in that frame in order to forward all these updates. To address this, we simply leave some headroom in order to tolerate some collisions. For example, we only advertise 1/2 of a forwarder's capacity. This means that drops, although they still might happen, will happen rarely and will probably only cause losses for a single frame because remember, each subsequent frame of the multicast tree will change by randomly selecting new trees. So collisions, when they occur, are unlikely to persist over time. And this is okay for game because previous user studies have shown that a small amount of losses is generally tolerated and is imperceptible in affecting gameplay. Of course, the main question we want to answer is whether this approach can deliver enough updates on time in order to satisfy fun gameplay. As mentioned before, this means delivering about 90 to 95% of updates within about 150 milliseconds, as shown by previous user studies. To evaluate our approach, we implemented it in Quake 3, and like previous work, we use synthetic large-scale game workloads in order to simulate small-scale capture the flag games, which were based on real players playing capture the flag.
So on the last slide, you can still actually validate the peak forwarding capacity, right? So this 5 to 10% loss is actually averaged over runtime window.
Right.
You can still, so if everyone takes up the same forward, you can actually drop. You can have actually maybe 99% loss instantaneous, essentially.
Right. So we want to maintain that the loss is low for even if lots of people are subscribed to you. Right. If a lot of players are, if your multicast group is very large, you still want the loss to be low, or like within this 5 to 10% range.
Yeah, my question is different. Essentially, how are you bounding the instantaneous, bandwidth demand for the forwarded? So how essentially you're saying, well, you pick randomly, but you still may have one bucket essentially getting a lot more hits. So you might actually see much more losses at some time instant. So
right. We actually don't do that. We just say that we tolerate that loss. If there's one frame where a lot of stuff gets lost, we just say we tolerate that. I can show you some results later after we get to the questions period. I don't have anything in the main talk, but.
Well, also, since you choose randomly differently each frame, that loss is not going to be sustained.
Right. Right. So I think he's asking about during a single frame, a lot of stuff can get lost. Right.
There's also the issue of that we use deltas that are.
Right. There's some other issues. There's some other details where we try to minimize the loss. So anyways, describing our evaluation setup. So finally, we basically simulated the network between the nodes using some empirical models, which I don't have time to go into here, but basically are described in detail in the paper. And basically, it's to simulate game hosts in a modern game environment on the internet. So here we show the percentage of updates which were received on time, averaged across several trials on the peers in the system, as we increase the number of players on the game on the x-axis here. The error bars here show 95th percentile confidence intervals, and the gray line here shows the amount of updates we want to receive in order to preserve fun gameplay. We see that the red line is always above the gray line, as shown here. And so from this initial simulation, we believe that enough updates are delivered on time up to scales of 1,000 players, which was our original goal. So based on our initial user study and these simulation results, we conclude that Donnybrook seems to be able to preserve the fun in large-scale, high-speed, peer-to-peer games. We use two main techniques to do this, using intersets to reduce bandwidth demands and a novel update dissemination strategy in order to handle heterogeneity. We're currently working on large-scale deployment, so hopefully you'll be able to download our game soon and start playing with each other. So that's the end of my talk, and I'm open for questions now.
So for the user study, was it between subjects or within subjects design?
Not quite sure not familiar with that terminology.
Were the same participants given all three treatments, shown all three versions of the game, or were you getting scores from different sets of participants each who only got to do one thing?
Different sets. So each pair only compared two of the three versions.
Neither of the two.
Neither of
the two alternatives.
No, it was one of them. It's a within subject design. The same subject is subjected to both treatments.
In pairs.
And we had two types of within subject experiment. One type was they were comparing low BW to low BWIS, but it was always the same subject subjected to both treatments. And some different subjects were subjected to low BWIS and high BW. That's called within subjects, right? Where the same subject is subjected to both treatments.
So then did you randomize the ordering?
Yes, we had half start on one, half start on the other, half the pairs.
Okay. And did you do a statistical test for a difference, or did you just do error bars? Was there a t-test or anything like that?
Yeah, we did the t-test, and it's significant.
Okay.
So, is there anywhere about is correctness? Because
Correctness.
I pop your field in
Right.
and I go from a 1 second to 20 second, but in that time span I shoot you. And so you have a kind of an unexpected gameplay flow.
Right. So there definitely are artifacts using our intersect technique. So if we incorrectly estimate who you're paying attention to, and say you shoot someone who's not in your intercept, then they'll be incorrectly displayed, and there might be some artifact. But of course, the end goal is to preserve fun gameplay, and we found that the players didn't seem to notice. I mean, part of it might be because a lot of stuff's going on, so you can explain away some of the artifacts.
Can you describe the gameplay histories of the subjects in the test?
Sure. Actually, have a slide for that. So most of them were fairly familiar with first-person shooter games. And they were all basically interns at Microsoft while we did this approach.
I'm just curious. Asking you to speculate a little bit, but if you'd taken a group of hardcore Quake players who were used to the game, I'm guessing the artifacts would be much more noticeable to those groups who had expectations about gameplay versus people who were familiar with first-person shooters in general.
Right.
Well, that's any FPS. So if you take a bunch of Halo players and put them in Quake, they have no expectation of how the game should be played.
Right.
So I know you're probably arguing that the trade-off of artifacts is worth it because you can scale the game. You can scale the game more.
Yeah. So that is true, and we did, even just based on this test, we did see if there was any correlation between experience and see if their score they gave or how much time they played in each game. And there was a small correlation, but it's not very significant.
And there was one case that I recall of somebody noticing an artifact. Somebody saying that, I can't remember exactly what it was, but it's an instance of somebody like jumping behind somebody and shooting him and saying, well, that couldn't have happened. I know there was nobody there.
Right.
Yeah.
So yeah.
So you've got interest, which seems to be a non-binary variable. It would seem to be something that's
Right.
on the scale, and you've got frequency, which is also something that's very easy to scale up or down. Why did you choose to do this in a binary fashion rather than just ratchet up frequency with interest?
Mostly for simplicity, just so it makes it easier to say you're in one category or another. Also because in games, it makes a little bit more sense this way because there's only one other player you're paying very close attention to. That is the person you're following, the person you're trying to shoot, and the person you're currently in combat with. And the other players in interest set we currently put in there basically sort of as a fudge factor for this approximation. So, but there are other cases where obviously we could maybe improve the system by making this a more continuous variable.
There's another factor as well, which is the behavior. The way we handle the players is actually quite different in the two cases. Jeff just talked about it very briefly, but the players you're getting continuous updates with, the game treats just like the game ordinarily does. It's, you get an update, okay, that's where you are, that's precise information about you. The information that you're getting relatively infrequently, we're doing this more complex client-side processing with receiver-side processing with, we're using an artificial intelligence agent that is guided by the information we're getting remotely in order to approximate what you're doing. And we found that in that mode, 1 second updates are sufficiently frequent. So if we got like updates every other frame, it wouldn't make the AI all that much better, but it wouldn't be sufficient for you to actually have precise information about where somebody is.
But you're also tracking all the objects from those remote players too, missiles, canisters, whatever, bullets, so.
Bullets are instantaneous, but missiles, yes.
Okay. So bullets from a long distance away are instantaneous?
Bullets are instantaneous and quick.
That actually leads into my question. So I was wondering about the difference between hit scan weapons, like the instantaneous things, like the railgun, and projectiles. I saw you had weapon-specific optimizations for the railgun. Is that based on the view, or is that actually switched on weapon characteristics?
It's basically based on the weapon you're currently holding. So we basically just changed the weights of the 3 metrics. So I showed you 3 metrics that we just weight that we add together in order to determine who you're focused on. So basically, based on the weapon you're carrying, we just changed the weight of each of the metrics.
And when you're handling things like rocket launchers, do you do the interest sets based on the position of the rocket or the player?
Right. So right now we don't, or for the user studies, we actually didn't have any special technique to deal with the missiles. We basically based the missile, or we basically had the missile be in the same interest set of the player which shot the missile. So if you focus on that player, then you get frequent updates from the missile, otherwise not. In Quake 3, this turned out not to matter so much because missiles follow a straight line trajectory. So as long as you get one update, you know where the missile is going to be.
Could you talk about the guidable AI stuff? Because I'm thinking we probably want to put that in the talk. And so
How much of the benefit from fun gameplay is derived from the AI changes you made?
Sorry?
Are they separable?
They probably are separable with appropriate experimentation. We did not do that breakdown.
And that's part of the fun gameplay is noticing the things in the far distance at a smooth arc versus a jumpy arc. And you could make that to some of the same optimizations with velocity data rates without having interest sets. So it'd be interesting to know how much of the contributions from that.
Right. So the problem with just doing this approach, using smoothing out the players with AI, is that we still need some ways we still enforce that interactions, for example, when one player modifies another player, that those incur instantaneously, that you immediately send those updates, and when you shoot someone, they explode, because those were the most jarring artifacts which occur in the game if they didn't occur immediately. So if you displayed someone, if you only used AI, then those interactions would still occur could still occur in a inconsistent fashion. So we didn't do any sort of formal study of like how much each approach contributed, but just anecdotally we saw that using that approach is not sufficient.
Well, I guess the stronger statement is we think you really need all of them. That if you don't have the guidable AI, people are going to say, hey, what the heck's going on back there? All these things are jerking all over the place. If you don't have the interest sets, then the short-term interactions, the interaction with somebody you're directly shooting at isn't going to be right because you've got this potential 1 second lag.
So I mean,
our speculation is that you need both, but yes, we haven't scientifically evaluated.
Well, if you had the time to make that argument in the talk, I was just saying, it kind of hung with me throughout the whole talk. Okay, you're doing this AI smoothing, what's the effect? And you can just address why it's insufficient. We think it's insufficient.
Okay.
One more thing that might be worth looking into in the user study is to see whether there was a different score differential between the folks who did the good experience first and the bad experience, and vice versa, because I assume you're having them score it right after they play the game, not after they've played both?
After they played both.
Oh, you're asking them after they've played both?
Yes.
Oh, because then they know you're rating, if you do that, that's very dangerous, because then they know, oh, well, what was different between these two things? oh, they want to see whether the speed was better. So they're actually going to try to, you have to worry that they're going to try, this may contaminate how they actually felt about the game, whereas if you ask them immediately after, they would just be rating how they liked the game. So they essentially at this point know what you're asking is, how much do you want us to deliver you a fast, smooth experience?
Well, we're trying to
We're
actually
trying to
replicate
compare.
the behavior. Yeah, sorry.
So what we're trying to do is replicate that same experience that you generally experience on the internet right now when you choose between two different servers. We allowed them to switch back and forth between the servers, between the two different versions when they're during the gameplay themselves, during the gameplay itself. And that's basically the same experience. Now, if you want to choose a server, you try a server. If it's crappy, you try another server, or you switch back if that one seems better. And what we want to do is not actually get an absolute score for how fun is this version, but a relative score, like which one you like better, is what we're trying to determine.
Sure. So I think you then need to limit what you can say to the fact that they were able to differentiate the quality, not that it not that it had any difference you can in any way measure other than that.
Right. So it was the case that some players were perfectly satisfied with a low bandwidth choppy game. Yeah. So yeah, we're not going to say that all players that found that unfun. It's just that players preferred the interset version.
That question. Another thing you could probably say when people object to the survey coming afterward is that was only one of the metrics that we did.
Right.
There were also metrics that we evaluated during the game, like how long they played each one, not how long it took them before their initial switch, before they even saw what the other game was like. That was only one of 4 metrics that we had. Okay.
Right. So basically, at some point they voted. They say, okay, I don't like this anymore. I want to switch to the other version. And this graph here shows the amount of time they took them to do this before they actually saw what the other version was.
So do games like Quick do any sort of cheat detection? And if so, does this have any effect on it?
Games like Quick, these days they do amount of cheat detection, mostly in software. We currently obviously increase the potential for cheating using our approaches, but generally all peer-to-peer approaches will increase the potential for cheating. We think that existing defenses, such as those that can be deployed on consoles, might be able to defend against software cheats using trusted hardware and encrypting packets between the sources between the nodes in the system. Obviously, if you can modify the actual game itself, then it's very hard to prevent cheating in Donnybrook or any game, actually, because if it's peer hosted. Of course, Donnybrook is uniquely vulnerable to some other cheats that other games might not be vulnerable to, because you can do traffic analysis and maybe even block packets that are coming out of your machine, even if you trust the software running in the machine itself. For example, you can determine who's in your interest set by seeing who you send packets to. Right? That's one of the cheats you might be able to do using Donnybrook. And we're currently working, or Jay and JD are currently working with some interns on ways to try to defeat this by doing choosing forwarders in an intelligent fashion, so you can't infer this information just by who you send packets to. And we can punish players if they drop too many packets or don't meet some expected rate.
So Jay, suggest you say a little bit about how the AI works, and you might even want to add that to the talk.
Yeah.
Right. So I used to have, I can show you the slide I used to have. I used to have this slide, or some of this slide in the talk, which basically shows how guidance worked. And we used, one of the techniques we used to smooth the transition between the guidance.
Well, you want to present the slide?
Oh,
So
okay.
you know,
So basically with the unfrequent updates, that is the updates we send to people not in our intersets, they only get those updates once every second. And if we were just to replay those state snapshots every once per second, they appear very choppy, as we saw in the video earlier in the talk. In order to prevent that, because that would draw players' attention to things they are not paying attention to because it appeared very jarring, we basically use, instead of updates, we use something called guidance, where we send basically predictions of where we think the player will be within the next second or so that we can use a smoothing technique in order to extrapolate where those players will move to. And we basically use existing AI routines within most games today, such as pathfinding code, in order to smooth these transitions. For example, in Quake 3, we just use game simulation to do the prediction, and we use the pathfinding code for existing AI computer players in order to smooth the transitions between these positions that were given in the guidance. And there's a couple other fields we extrapolate, but that's generally the approach we take.
With this guidance, have you tried to measure
the error?
Whether, yeah, like if you just extrapolate their current path versus using this AI, does it result in shorter updates when you actually get real data from the player about whether?
So the update where the guidance itself is not actually any bigger. We only extrapolate where we think they'll be in 1 second, and then we basically tell the AI to move to that position, so that the next time they receive an update, if the prediction was accurate, then they'll be able to start from the correct position.
It's just a matter of you're basically smoothing the path by using the AI to take a more realistic path from point A to point B.
Right.
I guess you could then measure, when next time you get an actual update from the player,
how far off
whether that route you chose was actually reasonable.
Right.
You might not know the route, you just know the ending point, how much you jump to the ending point that you expect it to be.
Right. Exactly.
Where you are.
Exactly.
Right. So yeah, we could do that. We have some measurements of the error, but we don't actually. I don't have them in the talk here. Basically, most of the time it wasn't that high, but sometimes it was pretty much unbounded. So when the error gets big enough, we basically just say, oh, we messed up, and then we snap the player back to where he's supposed to be.
So if you mess up, you don't snap them. You just.
If they're within some threshold.
If they were within some sort of threshold, then we just keep them moving this way. Yeah.
Okay.
Yeah.
And then once they're off screen, it just resets and you can bring them on again.
Sure, we don't actually wait until they're off screen. We just do some threshold. Because even if they're off screen, it could be jarring to like spin around and see someone and not see them the next time you spin around. So.
You're actually playing the game.
All right, I guess we've finished with questions. Thanks.